we are going to be going in reverse again, and just like we went from f prime to f, in this particular case, case 5, we're going to be going from f double prime to f prime. It's the same exact process. We're kind of going from a function's derivative back to its original, but in this case it's just f double prime to f prime. Again, it's the same thing as going from f prime to f, which is what we did in case 4. Here we have our graph. In fact, let's take a look at a more cleaner version. And I've just noted some things here about the graph, where it's decreasing, where it's increasing, some weird changes like corners and holes, also where it has a horizontal tangent, it goes from increasing to decreasing, even where it's above and below the x-axis. All of those things are going to contribute from going from f double prime to f prime. So let's read this together. Following is the graph of f double prime, the second derivative of f of x. Use this graph of f double prime to sketch f prime, the derivative of f of x. So again, it's actually exactly the same process as going from f prime to f. I wouldn't see it. Actually, the steps are exactly the same. It's just a matter of notation, more or less. So again, here's our graph, f double prime. How can we graph f prime? We're going to follow the same exact steps from case 4, going from f prime to f. Let's take a look. First of all, we want to determine where f double prime is negative. We can see by some color here. It's below on this interval, minus the whole, of course, and it's below the x-axis on this entire interval right here. It's a solid point. So, there will be a hole right there in between those two values. It should have notated that. In fact, let me change that real quick. Okay, so from negative 6.5 to negative 3, this f double prime is negative, and from negative 3 to negative 1.5 it's negative. Also negative from 1.5 to infinity. So what does that mean about f prime? Well, that means it's going to be decreasing. And that's because the slopes of the tangent lines will be negative, and therefore f double prime, which is derivative, will be negative, or below the x-axis. So f prime will be decreasing when the interval is negative 6.5 to, let's change that again. Negative 6.5 to 3, negative 3, negative 6.5 to negative 3, negative 3 to negative 1.5, and 1.5 to infinity. F prime of x will be decreasing on those intervals because f double prime of x is below the x-axis there. In the same way, we want to figure out where f double prime is positive. So from negative 1.5 to 1.5. And I must have forgot one more. From negative infinity to negative 6.5. So remember, wherever f double prime is positive, f prime will be increasing because the slope of the tangent lines will be positive, which means f double prime will be above the x-axis, or positive. So f prime of x will be increasing on these intervals. Now remember, we're going to be putting increasing, decreasing, and concavity together in one chart so that we can better sketch f double prime. Since we're going backwards, it's much easier to do it that way. Step 5, where does f double prime go from positive to negative? We can actually circle that. It's going to be at negative 6.5 and at 1.5. Now why is that? Well, that means that f prime is going from increasing to decreasing, which means it's a relative mass. So f prime of x will have a relative max of negative 6.5 and 1.5. In the same way, we want to figure out where does f double prime of x go from negative to positive. And that's actually only at one point at negative 1.5. That means that for f prime, the slopes of the tangent lines, the tangent line will be going from positive to negative, or negative to positive, which is means it's going from decreasing to increasing, which means it has a relative min. F prime of x will have a relative min of negative 1.5 because f double prime of x crosses from negative to positive there. Again, for the tangent line of f double prime, it will go from a negative to positive. So we'll have a relative min. Step 9, where does f double prime have asymptotes? Nowhere. Now again, as a reminder for step 10, that would mean that f prime, which is we're going to call the antiderivative very soon, meaning the reverse of the derivative, would have cusps of vertical, tangent, and asymptote, because when that happens, that's places where the slope of the tangent line approaches infinity, and therefore its derivative would have a vertical asymptote. Next, where does f double prime have a hole? It has a hole right here. I mentioned in a previous video that there would be an abrupt change in the tangent line. Not really. More clearly, we just know there's going to be a hole in the original. Because if there's a hole in the original, that means that the derivative or the tangent line is not going to exist. So it's likely going to have a hole too. Now it is true though that if you have a v like this, let's say this is f prime, f double prime is going to look like this. So if you have a jump like that, that means your tangent line abruptly changed, and you're going to have a sharp edge. Now in this case though, in the case of our graph, that actually didn't happen. The tangent line goes, when you're talking about, okay, so the y value goes from -7, just has a hole, and then continues to -7. So that means the tangent line of f prime would basically stay at -7 and would just have a hole there. So if you had a jump like this, this would indicate a sharp edge in f prime, but that's not the case. So we're just going to have a hole for f prime here. F prime has a hole at x equals -3 because f double prime of x has a hole there. All right, where is f double prime of x decreasing? Let's take a look. It's going to be going down here, be going down there. So on these intervals, now again, wherever f double prime is decreasing, if you go one function up, f prime, that means that it's going to be concave down because the slope of its tangent lines are going to be decreasing. So f prime of x will be concave down on the intervals -infinity, -3, and 0 to 3 because f double prime of x is decreasing. In the same way, we want to figure out where f double prime is increasing. That's only on one interval. -3 to 0. This is should not be there. So from -3 to 0, it's increasing. Now, I'm glad I kind of had that because I do want to mention one more thing before we move on. After we talk about this, and I want to mention one more thing. So wherever f double prime is increasing, f prime, which is this antiderivative, the reverse derivative, will be concave up because the slopes of tangent lines will be increasing. So f prime is going to be concave up from -3 to 0. Here's the other thing I wanted to mention. We showed that it's concave, that f prime will be concave down here, concave up here. But what about here where the graph is flat? It will be neither. F prime will actually be, we actually need to make kind of like a separate page here. Well, we'll do it on the same page. F prime will be neither concave up or concave down. Okay? It will be a line. So whenever f double prime is flat, f prime will be a line. Or you could think of f prime as a line. If f prime is flat, f will be a line. And a line does not have concavity. You know, if you think about a straight line, it's either concave up or concave down. It has to be curved. So f prime is actually going to look like this on this interval. Okay, if you think about it, the slope of the tangent line would be negative, and it would stay constant, which is exactly what's happening here for f double prime. So if we go in reverse, we can see f prime is going to look like that. Okay, step 17. Where does f double prime of x have a relative extrema? You can see it has one right here. Now it does not, so at x equals 0, it does not have one here, simply because there's a hole. But pretty close, right? So remember, wherever f double prime of x has wherever f prime of x has a relative extrema, f has an inflection point. So in the same way, where f double prime of x has a relative extrema, f prime of x will have an inflection point. So again, if you haven't seen the previous video going from f prime to f, make sure you watch that because it's exactly the same steps. Case 4 and case 5 are the same. So f double prime of x is going to have an inflection point at x equals 0 because there's a relative extrema for f double prime. So relative extrema for f double prime means an inflection point for f prime. So now we're going to plot our points. Now again, you might be wondering, what are the y values? Okay. Now we have a relative extrema at negative 6.5. We know we have one at 1.5. We know we have an inflection point at 0. We know we have a relative min at negative 1.5, hole at negative 3, and as we talked about before, at 3, the concavity is going to change, okay? The concavity is going to go concave down to a straight line. So I'll put a black point there because we know it's going to be concave down here, but then it's just going to become a straight line after that. So it's kind of a special point where the concavity actually changes from concave down to undefined concavity or straight line. So as I did before, since we're going reverse from f double prime to f prime, I simply went back and looked at my increasing and decreasing levels and grouped them with my concavity levels. And you can see that they're kind of different. And so when you put them together on a chart, you want to make sure you get everything clear. So as I start to connect my points, I'll notice that go from negative infinity to negative 6.5, it's increasing and it's concave down. So I'm simply going to go like this. Okay? And then for my next interval, negative 6.5 to negative 3, it's going to be decreasing but stay concave down. So I'm going to go back and go concave down but decrease. So you can kind of see why I put my point negative 6.5 so high, because I knew it would go from increasing to decreasing, and then I have to go concave down back to my hole. Now again, you could move all these points down and shift them, but at the end of the day, you have to make them so that your points connect and make sense with your concavity and increasing, decreasing. Next, we're going to go from negative 3 to negative 1.5. We know it's decreasing and concave up. And so I'm going to start to go, oops, didn't mean to do that. I'm going to start to go concave up, but still decreasing. Now, from negative 1.5 to 0, it's going to start to increase and remain concave up. Then we have an inflection point, and we know that the concavity is going to change again, and it's going to still increase, but it's going to go concave down. And that's from 0 to 1.5, increasing concave down. Then from 1.5 to 3, it'll be decreasing and concave down. So it'll remain concave down, but it'll decrease. And then this is that part we were talking about. I might have to sketch this a few times to get it right. At that point, we said that the f prime will be a line because f double prime is a constant number. So that means the slope of the tangent line of f prime will be constant. But it'll be negative because it's negative 7. So actually the slope of our line for f prime will be negative 7. So it'll be a relatively steep line. So we can kind of just keep going with this line and just make it as close to a level. It's hard for me to draw a line. As close to negative 7 as possible. That might not be steep enough, but again, it's just a sketch. So there you have it. There's our graph of f double prime given f. Here's f double prime, and I'm sorry, here is f prime, okay? And here's f double prime. So we went reverse. We went again from f double prime to f prime. F prime is called the antiderivative. It looks kind of completely different, but we use concavity, increasing and decreasing, relative min and max, inflection points, all of that stuff to sketch the graph. So that's it for this lesson. Going in reverse, make sure you follow these steps to get an accurate graph. If you have any other questions about this, let me know.